talk about a super important topic when dealing with two-dimensional kinematics, and it's this idea of the independence of perpendicular vectors. It's something that when we're dealing with objects that are flying through the air at some launch angle, we're going to have to deal with a horizontal motion as well as a vertical motion simultaneously. And in doing so, how do we deal with that if we're launching an object at, say, an angle of 52 degrees? And the answer is, independence of the vectors sure helps out a lot. So let's start off with the big aha moment, that perpendicular vectors are independent of each other. And that's a monster statement to make. Now, what do I mean by that? Well, let's say that I throw a baseball in the air at some angle. There is a component of the velocity that is moving vertically, and there is a component of the velocity moving horizontally. The cool part is the horizontal motion is independent of the vertical motion. This is why in one-dimensional kinematics, we're able to deal with things up and down without having to even think about side to side, because this up and down motion is completely independent of the side to side. Now again, in one-dimensional we were talking about straight up and down, but what if it was on a little bit of an angle? Well, the answer is it didn't matter overall. If you do a graph of distance versus time of an object that's thrown straight up versus an object that's thrown on an angle, they both make a parabolic shape. So in theory, they're both the same things, and the one-dimensional case is just a special case of the overall two-dimensional idea. So this is a really, really big deal, that we can take some sort of resultant and break it up into its components, or vice versa. We can find the resultant velocity or whatever vector just based on the idea of doing vector addition. So again, if I use the projectile as an example, if I have the horizontal velocity and I have the vertical velocity, I can add those two vectors up because they should be perpendicular, and the resultant that I get is the actual velocity with the given launch angle. So don't forget that the resultant vector has a magnitude and a direction. This is important. That means we're going to have to find the angle that this resultant makes in this new right angle triangle that we're going to create. So be sure that you, whenever we talk about the resultant, that we also include some kind of direction in terms of degrees. And finally, and definitely most importantly, we don't use plus or minus when we're dealing with resultants. When we're dealing with a linear motion, one-dimensional, positive can mean to the right and negative can mean to the left, and these ideas. But when we're dealing with a two-dimensional situation here, we really need an angle to help us explain what the direction really is. So be sure that when we're dealing with these cases specifically, that you're going to be finding the angle in the end. So let's deal with pretty much a classic case here. After escaping from a maximum security prison stockade, the A-team, oh I pity the fool, is trying to travel north across a 350-meter river in a speedboat. The boat can travel at a speed of 25 meters per second in still water, and the river flows to the east 11 meters per second. So the key to all these types of questions is being able to draw the picture. You have to draw the picture. And let's take a look at the information that they gave you. They tell you it's 350 meters wide. They tell you that the boat can travel 25 meters per second in still water. That's key, because what happens in still water, whatever direction you go in, is exactly the direction you're going to travel. And that's a key feature to consider. And finally, the river flows east at 11 meters per second. Well, our picture had better represent that as well. So these are the key ideas. Let's see how this plays out. So, first question we'd ask is, well, what is their total resultant velocity if they point the boat directly north across the river? So let's draw the picture here. And on the top and bottom, these will be the banks. And we have nice water because it's flowing. Now, which way is it flowing? Well, it told you that it was traveling east at 11 meters per second. So if I'm going to draw this vector triangle now, I'm going to draw a vector that goes east at 11 meters per second. Now, we were also told something else. We were told that in still water, the boat could go at 25 meters per second. Well, what does that mean? That means if this river wasn't flowing and I pointed my boat straight across the river, it would go at 25 meters per second. Well, if you'll notice now, I have a vector that's pointing straight across the river, and I have a vector that's pointing with the river, that means these two vectors are perpendicular to each other. And wouldn't you know it, look what I've done. I've added the vectors tip to tail, which means the resultant is this vector right here. And when we talk about the heading, this angle right there is going to be the heading of the boat. So what is their total or resultant velocity? Well, this is simple. It's a right angle triangle. We have the two sides. That sure sounds like the Pythagorean theorem to me. So I'll label this V sub r. And what do we know? We know V sub r squared is equal to the V river squared plus the V boat squared. And when that's the case, we can plug in the values. We know that the V river is 11 meters per second squared plus 25 meters per second squared, and that still equals VR squared. Well, we need to take the square root of both sides. Don't make a rookie mistake and just square root each number individually. So VR is going to equal the square root of 11 squared plus 25 squared, and that's going to equal 27.3 meters per second. So we have our velocity, and it was just as simple as the Pythagorean theorem, which most of you learned in grade 8. So we have the resultant. That's awesome. The problem is it's a vector. We have to find that angle theta. What does that mean? That means we have to go to the battle cry, SOHCAHTOA. And the fact that we have all three sides means that we can use any trig function we want. My advice to you is the fact that we were given two of the values, use those, because what if you made an arithmetic error on VR? So it's easier if we just say that the tangent of theta is equal to the opposite over the adjacent, which means that theta is equal to tan to the minus 1 of 11 over 25, which is going to give us a value of 24 degrees. In physics, by the way, for those of you that are in grade 12 dealing with radians already, we almost always in kinematics use degrees as our angles. So we have the degrees, we have the velocity. That means the actual answer is 27, and I'll do it to the sig figs, 27 meters per second, 24 degrees east of north. Remember, this is north, the angle is to the east of that, so east of north is acceptable. And there it is, my friends. That's the answer to our first question. So the hint at the bottom, of course, is add the two vectors using vector addition and find the resultant. Tip to tail was crucial, Pythagorean theorem, and then using trigonometry to find your bearing angle. So that's part A. Let's move that along now. With part B, how long does it take to cross the river? Well, now it's just a matter of deciding which vector is the vector that we want. So in this case, to find how long it takes to go across, well, we're not talking about accelerated motion, so velocity equals distance over time. And in this case, we need to solve for time. So time equals distance over velocity. But there's a problem. We have two different velocities, and we have potentially some different distances, because there's going to be a distance traveling down the river as well as a distance traveling across. But we're told that the distance across the river is 350 meters. So we can rewrite this as the time is equal to the distance to travel in the y direction divided by the velocity to travel in the y direction. Well, how do I get these y's? Because I have drawn the picture specifically to show that these should be 350 meters divided by 25 meters per second. And when we finish the calculation, we end up with 14 seconds. So in this case, to find the time it takes to cross the river, all we need is the vertical component. So don't use the resultant in that case. It's not necessary. So in general, the width of the river is the displacement in the y direction, so we only use the y velocity. That is the general case. So you're going to catch a lot of these types of questions. Make sure you're aware. So part C is how far downriver do they end up? Well, again, if we use velocity equals distance over time, this time let's rewrite this as the distance in the x direction is equal to vxt. Now how can we do that? Well, it all comes down to this idea that the perpendicular vectors are independent of each other, and regardless of how fast it's moving vertically, it is independent of how fast it is moving downstream. So in this case, the horizontal vector is the velocity of the river, and that's 11 meters per second. And the time it takes in its trip, well, we're trying to find out when it gets to the other bank, how far down did it go? Well, that's just the time that we calculated in B. How long did it take to get across the river? At some point, you're going to end up somewhere down the bank, so the time is the same, in which case we're going to use 14 seconds, and that gives us 150 meters. But now this is the actual downriver, and when we say something like that, we better add some sort of direction to this. So in this case, this is in the east direction, because again, it's getting pushed downriver. If we had established that downriver was to the west, then in this case, that would be west. So read the question carefully. If they don't give you a direction of the flow, you have to impose it yourself. Okay, so in general, how far they travel in the x direction depends only on the x velocity and time. Here it is in a nutshell, your independence of the perpendicular vectors. So let's do one more example here. And the law caught up with these boys, and they're wading downriver on the other side, and we might ask a question like this. At what heading should they point the boat so that they can land safely directly across the river? So this one's a little trickier, but if you take a look, let's start off by drawing the picture. So again, we have our banks. And in this case, what are we doing? Well, we know that this is 350 meters across. We know that it is flowing at 11 meters per second. And we know that the resultant we want in this case is directly across the river. So in order to do that, we need to point our boat this direction at some angle theta. Now, what is the magnitude of this vector that we've drawn? Well, it's 25 meters per second, because that's how fast the boat travels in still water. In the first example, we pointed it straight across the river and let the river push it down. In this case, we're pointing it up the river and we're letting the river push us vertical. But in order to do that, the velocity of the boat would still be 25 meters per second, but the resultant right here, well, that's going to be a different value. And that's the key right here. So the resultant velocity is just equal to Vy. You'll notice, again, in order to make it go directly across river, it has to be perpendicular to the river's velocity vectors. So now we have the picture set. Let's solve this bad boy. In this case, we need to find what heading they should point, and that equals angle. So we need to find the angle. Well, how do we do that? Well, in this case, what are we given? We're given the opposite side, and we're given the hypotenuse, so that's sine theta, and that's equal to 11 over 25. So theta is equal to sine to the minus 1 of 11 over 25, which is going to give us an angle of 26 degrees. Now, which way is that 26 degrees? Well, that is to the west of north, so west of north. Okay, so in this case, we're just looking for the heading. So we're going to point our boat that goes 25 meters per second in still water at 26 degrees west of north, and the resultant velocity should be directly across the river. And as it says, the boat's velocity vector will point up the river, and adding the river velocity vector will give the resultant that points due north. This is the general solution that I'm giving you in these yellow notes here. So I'm giving you a specific example, but in general, this is how you solve these questions every time. So what now would we do if I say, how long will it take to get them to cross the river at this heading? The only way we can know that to cross the river is we have to use velocity equals distance over time and solve for time. So time is equal to distance over velocity. But we're talking about going across the river, which means we can rewrite this as the distance in the y direction divided by the velocity in the y direction. Now, we haven't solved for the velocity in the y direction yet, and if you look at your previous diagram, we have the hypotenuse and we have one side, So what can we say? Well, we can say that V river squared plus V resultant squared is going to be equal to V boat squared. Notice how that's different than A, and that's because our resultant was when we took our velocity of the boat and put it perpendicular to the river. In this case, we didn't. We put it on a heading, and our resultant velocity was actually the perpendicular. So this is how you have to write it out, and we're solving for this, which means VR is equal to the square root of V boat squared subtract V river squared, plugging in the values, square root of 25 squared minus 11 squared, and that's going to give us a value of 22.5 meters per second. So we have our Vy, we know our dy because it was given in the question, so now we can solve for t. 350 meters divided by 22.5 meters per second, which is going to give us a final time of 16 seconds. So in 16 seconds, we will get across the river, directly across from where we started, because we pointed our boat at a heading of 26 degrees west of north. So there you go, my friends. These are a little tricky. You'll notice that I always draw a picture, and I'm always very diligent in the way that I'm doing these questions, so be sure that you understand the independence. They are always at right angles of each other. As long as you do that, you have the Pythagorean theorem, you have right angle trigonometry, and you have the conceptual understanding of these questions. So good luck, and we'll talk to you again.